I'm going to go over the multiple choice part of the practice test for Unit 4. And just one thing I kind of found on the internet, there was lists of strong acids and strong bases, and I always think it's interesting that different books list different numbers of acids and bases. We have 8 strong acids, 8 strong bases. The other people have 6 strong acids, strong bases, and they're just leaving out a couple of them that are not quite so common. So like we have HClO3 and HiO4 in our list, and they don't have it here. They're not in over here on the strong bases. They're leaving out the rubidium, okay, that kind of stuff, rubidium and cesium, because they're just not that common. But other than that, everybody kind of agrees on the strong acids, strong bases. Okay, so let's look at these problems. So consider this equilibrium. Now, one idea I do think that you should think about when you're doing a multiple choice is don't look at the answers, okay? That, when you have a question, if you can, maybe decide what the answer is and then go back and look at the answers and find the right answer, as opposed to starting looking for the answers and seeing which one, looks like the right answer. So, answer the question and then pick your answer from here. So if I'm looking at this here and it says pick a conjugate acid-base pair, well, I know that my conjugate acid-base pairs are just, two things that differ only by one H+. So one thing has it with the H+ and the other without the H+, and that's my pair. So I'm looking for either H2O and H3O+, or HF and F-, and so I can knock off that one. Here's my answer. Okay, and I can knock off that one and that one. So I need something that's just different by one H+. Okay, number 2. A solution of ammonia and water turns universal indicator blue. That's basic. In this situation, which of the following is true? Okay, so if I have NH3 and I put it with water and it makes my solution basic, what that means is that an H is leaving my water and going over to ammonia, so I'm getting ammonium, and I'm getting hydroxide now. And so what is that? H2O is a base. No, it's a donor, so that's not even true. H2O is amphoteric. It's true. It both accepts and donates a proton, not in this case. So it can be amphoteric, but not in this case. In this case, it's acting like an acid. H2O is an acid because it donates a proton to NH3. That is the answer, because we just see it right there. And the last one, NH3 is a base. That's true because it donates a proton. No, that's where it goes wrong. So the answer is C. Number 3, methylamine is a weak base. When it reacts with water, what does it do? Okay, so we should do that. CH3NH2. When we put that with water, okay, it's a base. So again, that means the H+ goes over here. So we're going to form methylammonium, so CH3NH3 with a plus charge and OH-, and so there's the answer. CH3NH3 with a plus charge, and that's called the methylammonium ion, in case that comes up. Okay, number 4, a 10 milliliter sample of HCl solution was obtained. What's the pH of the solution if 90 milliliters of water was added to the solution? Okay, well, pH, if I just started from here, then I'd say, well, the H+ concentration is the same as the HCl, and the HCl concentration is 1 × 10⁻². Okay, that's a good thing to do, put it in scientific notation, because now I know my pH is 2, but I'm going to take my 10 milliliters and I'm going to add 90 milliliters, so now it's going to be 10 times more dilute. So my H+ is 1 × 10⁻3, so that means my pH is 3, and that's my answer. Okay, number 5. The Kw at 0 degrees is 0.1 × 10⁻14. So what's the pH of a glass of pure ice water at 0 degrees? Okay, so we have to kind of go back and know, what do we know about pHs? Okay, we know that the H+ concentration times the OH- concentration equals, now at 25 degrees it's 1 × 10⁻14. Here it is 0.1 × 10⁻14. Okay, so if I want my H+ concentration, I can see what I'm going to do is to take the square root, because this is both going to be x. okay, because water breaks up to give H plus and OH minus. So x squared equals 0.1 times 10 to the negative 14. So therefore x is equal to the square root of x squared is equal to the square root of that. Okay, so let me calculate that. And for that I get 3.162 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. No, 8. Okay, and I'm going to take the square root of that. No, I'm not. Yes, I am. I'm going to take the log of that, and I get 7.5. So the negative log of this number is equal to 7.5, and so my answer is B, 7.5. Phew. Okay, so it's using the information that we already know, okay, and that is that for water, that when we have water at equilibrium, okay, it breaks up and you get H plus and OH minus. And if I said, okay, I'm going to let X of this go away, then I'm going to have, X of this, and I'm going to make X of this. So at equilibrium, I have X times X equals 0.1 times 10 to the minus 14. So solving for X, I get that number, and then taking the negative log of that, I get 7.5. Okay, number 6, milk of magnesia has a low solubility in water and is used to neutralize excess stomach acid, hydrochloric acid. Which equation correctly represents the net reaction when milk of magnesia reaches the stomach? Okay, so the idea is you have milk of magnesia. Now that is a magnesium hydroxide, and magnesium hydroxide is not very soluble. That's why it looks all milky. And it's going to hit hydrochloric acid, which is a strong acid, so it's H plus and Cl minus is going to be dissociated, and my H's and my OH's are going to go together, so I need 2 of those and 2 of those, and you can see what's going to happen, and I'm going to form 2 waters, and I'm going to have magnesium chloride, which is soluble, so I'm going to have magnesium ions and 2 chloride ions. So my chlorides are going to go away, so I'm looking for something with magnesium hydroxide plus 2H plus, turns into 2 waters and Mg2 plus, and that looks like answer D. Okay, so going back, this would be okay if I had a strong base, and I don't. This is a molecular equation, that's not what I want, and this is just wrong. Okay, we're not going to make magnesium chloride solid. Okay, number 7, which of the following is not amphoteric or amphiprotic? So we need somebody, to be amphiprotic, you have to have a proton to donate, and you have to have a place to put a proton. So this one here with the N, okay, and it has an H, and it has an H, and it hooks onto a carbon, and it has that lone pair. This is good. Okay, so this guy is amphiprotic. That's not our answer, because it can donate and it can accept. Okay, we've seen water. We know water has ability to be amphiprotic because it has a proton it can donate to become OH minus, and has a lone pair where an H can go, so that's not the answer. Okay, certainly not going to be this one, because that can either accept a proton and become H2CO3, or lose a proton and become CO32 minus. So it must be NH4 plus, and it is NH4 plus because with NH4 plus, all of the sites where a hydrogen might bond, okay, have already been taken up, so there's no lone pair, so it has no way to accept another proton. So that's why it is not amphiprotic or amphoteric. Okay, number 8. We have 2 solutions were prepared and represented, and looking at them, we see here's somebody who is totally dissociated, and here's something that's mostly together. Okay, a few things are dissociated. So there's a couple pluses, a couple minuses. Okay, but so representation on the right, okay, so we're looking at this guy, represents which of the following. So we want somebody that's totally dissociated. Well, HF, that's weak. NaOH, that's going to be totally dissociated. H2S, that would be weak. NH3, that would be weak. So 3 of those were going to be, only partially dissociated. They'd be weak electrolytes. NaOH is the only one that's going to be totally dissociated because sodium compounds are soluble and they will totally break up. Okay, number 9, a sample of a weak base is placed in water. The pH is 11. When tested, what's the value of the Kb for the base? Okay, well, first little clue, we have the pH is 11. And if the pH is 11, that means that the H plus concentration is equal to 1 times 10 to the negative 11. And for us, I think we're going to need the OH minus, so we could say the POH is 3, or we can say the OH minus concentration is 1 times 10 to the minus 3 molar. Okay, so that's useful information. Okay, we want the KB for this base. Well, I think I need to write my icebox and all that, so I'm just going to use ammonia, because ammonia is a nice weak base. And I'm going to put water. And when I do this, this is liquid, I'm going to get NH4 plus, because I know it's going to accept a proton, and OH minus, and I'm not going to use the water values. I have a 0.1 molar solution, and I know that my pH is 11, so my OH concentration here is 1 times 10 to the minus 3. Okay, so that means this must be 1 times 10 to the minus 3, and this must be 1 times 10 to the minus 3, and this will be 1 times 10 to the minus 3, and I'm going to use up 1 times 10 to the minus 3, so I'm going to have 0.1 minus 0.001, okay, which is going to be pretty close to 0.1, close enough to get my answer. So my KB for this, my KB expression, is going to be this guy times this guy divided by this. So it's 1 times 10 to the minus 3 squared over 0.1. And so that's going to be 10 to the minus 6 over 0.1. And so that is going to be an answer of 1 times 10 to the minus 5. So those, the other ones are all going to be wrong. So I'm just going to, that's not really ammonia, but that's a good weak base for me to get my icebox done. I know these two because of my pH. These are the same as each other. And this is essentially 0.1. So just working this out, I get 1 times 10 to the minus 5. Okay, number 10. How do the amounts of these species compare when NaNO2 is added to water? I think this is a really great and difficult question. Okay, so if I have NaNO2, I have to recognize that. Okay, I got Na plus and NO2 minus. Okay, the Na plus, that's going to be neutral because it comes from the strong base. We don't care about it. If I added NO and NO2 minus to water, okay, then that is going to be a significant base. So here, I'm going to put my NaNO2 in water, solid, and it's going to break up. I'm going to get Na plus and NO2 minus. And then that NO2 minus is going to react with water, and it's going to reform the acid and give me some hydroxides, and that's why it's a base. That's why it's the conjugate base of nitrous acid. But I like to rewrite that, okay, because what's going to happen, this is not going to be a real strong, base. So it's going to be mostly NO2 minus in water, and we're going to get a little bit of OH minus and HNO2. Okay, and the other thing I have to think about is, this is a basic solution, so if I have a basic solution, I am going to have some H plus, but it's going to be pretty small, okay, because a basic solution means I have more OH than I have H plus. So, going back, for the first step, I'm going to have a lot of Na pluses. So the fact that my Na plus is in my first thing here, that is great, but some of my NO2 minus is going to react further. So these are not going to be equal. So I can knock off those two answers. So I know it's not C or D. And the other part is the other two both have H plus concentration really low, and that I agree with that. Okay, so I know it's either A or B. Now what happens? The NO2 minus is my next concentration. That sounds good. But my NO2 and my OH minus, those are going to be the same as each other, because every time one of these reacts, I get 1 and 1. That's kind of tied together. So that means my answer must be letter B, okay, because my HNO2 and the OH minus, those are going to be the same. And that's my answer. Okay, number 11. Suppose we have a 0.1 molar HF solution. Which of the following, when added, would result in the lowest F minus concentration? So to me, this sounds like a Le Chatelier's problem, because I say, okay, who's going to give me the lowest F minus? So that means I want my reaction to shift to the left. So I'm looking for changes that will shift to the left and lower my F minus. So nothing else is added. okay, that would mean if everything else here shifts to the right, then this would be my answer, so we'll keep that in mind. What if I added some HCl? Okay, well, I don't care about the Cl, it's just going to be adding H+. If I added H+, that would shift it to the left, okay, and that would lower my F-. So this is definitely a possibility that will work. Kf, well, I don't care about the K because that comes from the strong base KOH, so it's just a matter of adding F-. Well, if I add F-, that will shift it to the left, but I'm adding F-. Okay, so if I'm adding F-, that is not going to result in a low amount of F- because I'm adding F-, so that's no good. And I can knock off this answer A because answer B is better than that. And how about KOH? KOH, the only thing that's going to happen there is that, the OH would react with the H+, and so that would remove H+. And if I remove H+, that's going to shift it to the right to make up that H+, and that's going to increase my F-, so that's not going to be a good answer. So my best answer here is letter B. Okay, adding the HCl would shift to the left and lower my F- concentration. So it's a Le Chatelier's problem. Okay, number 12. Which of the following have the lowest pH? Okay, now I always have to stop and think. Low pH means the most acidic. Okay, low pH is acid. Everything lower than 7 is an acid. So the lowest is the most acidic. So who's going to be the most acidic? Well, whoever has the largest Ka. The largest Ka is the most product favored, the most dissociated, strongest acid. So looking at these numbers, 10 to -3 answer is going to be bigger than the other ones. So the answer is A. Okay, my most acidic is my largest Ka. Which of the following forms a 0.1 molar solution with the lowest pH? Okay, so again, low pH, I want the most acidic. Okay, so I want to get rid of things that are neutral, get rid of things that are going to make it basic, look for something that's going to be acidic. Okay, KBr, that's going to be neutral, okay, because K and Br both come from strong acids, strong bases. Okay, here I have acetate. Acetate is the conjugate base of the weak acid, so that's going to make my solution basic, but probably not the answer. NaNO2, same thing. Na I don't care about, but the NO2 is the conjugate base of the weak acid, HNO2. And the last one here we have ammonium. Okay, and ammonium is the conjugate acid of the weak base ammonia, so that would make my solution acidic, and we did that in class. So the solution with the lowest pH, most acidic, that's got to be answer D. 14. Carbonic acid's diprotic, which equation correctly shows the dissociation of carbonic acid's second proton? So I just took a second and wrote out the two dissociations. So H2CO3 gives off H+ and HCl3, and then that HCl3- can give off an H+ and Cl3 2-. So I need to find an answer that looks like that. And so if I put in water, okay, then I get answer C. So this plus water turns into H3O plus and CO3 2-, and that's the right answer. So I can recognize answer C. Okay, 15. Consider the following acids. Okay, I like this question. So here we have a couple of different rules going on. So ClO3 and ClO4, HiO3 and HiO2, and then I have to compare something with I's and something with Cl's. And the ones that I can compare are these two, because they both have 3 oxygens. So I rewrote them down here, and the idea is I can tell, because I have more oxygens, okay, that this HClO4 is going to be stronger than HClO3. The more oxygens I have, the more polarized that HO bond, and the more likely that H is going to leave. So this is a stronger acid than this one. Now, if I have HClO3 and HiO3, then my rule is the more electronegative atom, which is chlorine, okay, will polarize the HO bond more. So this is going to be stronger than this one. So this is my strongest so far. This is next strongest. This is my next strongest. And HiO3 and HiO2, well, more oxygens makes it stronger than this one. So this is my least one. So if I want to go from weakest to strongest, then I need to go this one, then this one, then this one, and then this one. Okay, so I need HiO2 my beginning. Okay, and I need to have HClO4 at my ending, so that didn't help. Okay, and in between HIO3, then HClO3, that looks like answer D. And that's the multiple choice portion of the test.